Every electrical engineer has a mental tool bag of component knowledge that they can use when creating new designs to ensure safe, reliable, and effective circuit performance. For example, resistors, capacitors, inductors, and even Schottky diodes. But to meet the increasing demands of commercial vehicles with zone architectures and complex power distribution architectures, that probably isn't enough. Join us for this interesting tech chat to discover some new tools like feed-through, ESD Safe, and even bendable capacitors that you can employ in your next design. Welcome to Tech Chat, sponsored by Mouser Electronics. On Tech Chat, we meet with engineering experts to learn about the latest technical innovations that are shaping and reshaping our world. Today, I'm happy to welcome Ryan Messina, Technical Applications Engineer at Kyocera AVX. Welcome to Tech Chat, Ryan.
Hi, thanks for having me.
Well, we're glad to have you here. What's our topic going to be for today?
Today, we're going to be talking about zone architecture and power distribution networks in commercial vehicles.
Well, I'm looking to get started on it, so let's jump right in.
Jumping right in, basically, there's two questions that kind of need to be answered off the bat. What is zonal architecture and why do it? A brief synopsis would be zonal architecture is essentially splitting up a vehicle into zones where you would have essentially an ECU at each zone in the vehicle. Traditionally, we would use a domain architecture, what's been used in the past and what's prevalent right now, where you have communication buses going all throughout the vehicle, all coming back to one main hub, which can be a little noisy. There's a lot of latency that comes with that, with so many signal lines crossing and the lengths to which they have to move. So zonal architecture, really, it just organizes the ECUs within a machine in such a way that there are multiple ECU modules throughout the various zones of a machine. It varies. It can vary by vehicle, by commercial type, whether it be your typical farming vehicles, your transportation vehicles, or even commercial, like just normal everyday drivers. One of the zonal architecture hubs might be interior cabin, your stability and safety, drivetrain, etc. Or farm vehicles, it might be, the human machine interface, interior, the drivetrain, safety, maybe a machine arm or vision optimization and control, etc. But the various ECUs throughout the vehicle might feed into a gateway that keeps track of the overall functionality of the platform. Why would we do this? There are several advantages that can be realized with zonal architecture. The first is that ECUs get more processing capable because basically you're breaking up each zone of the vehicle and they have their own dedicated ECU or a zone module. You can kind of use that interchangeably. Your zone module will be your ECU, and they can handle the tasks at those specific zones real time, right away. So you don't have to have that latency or that length of signal lines going and have those delays that come with that long travel distance. You can also move power trees directly to each module. So you have dedicated power at that ECU, at that module. So everything can happen in real time, much faster. You basically create local power supply or distribution module in each zone. Ultimately, you can make a lighter, less wiring. Therefore, that would be cheaper harness that improves fuel efficiency, handling, performance. And then also you have processing power next to the action of a specific zone, which, like we said, allows for higher speeds and less latency.
Well, Ryan, it seems like this is going to be impacting a little bit of everything in the car. Just you talk about latency, you talk about real-time control, the power distribution. So it's a pretty monumental shift in how the electrical system of a car is being developed.
Right, 100%. So you're going to see a lot more just optimization, and maybe more functions are able to be added because there's additional power trees that are available at specific zones. So it's pretty exciting stuff. What we can see here is kind of a broken down farm vehicle or Class 8 vehicle. In there, you can see where you would break each zone of this vehicle down. And then within that zone where you see zonal modules, that would be an ECU essentially. And that ECU can control the body, powertrain, connectivity. All of those things are being controlled for each zone by that zone module that's there. And then they can talk and then parse data to the central gateway if needed. If there's a sensor or something within that zone that needs to be accessed in the central gateway so that you can have, an application run, or it needs to talk to a different zone, that central gateway is the main hub, like it is in a traditional domain architecture. But this way, if there are other periphery things that don't need to go to the central gateway or don't need a different module or sensor to operate, they just operate on their own out there in space. So it really just optimizes kind of what's going on. But this specific example, it shows a complex piece of farm machinery optimized with zonal architecture. There can be many more zones than what you see here, than 4 zones. But regardless, you have a zonal architectural module, basically an ECU, like said before, and drive electronics to the powertrain, maybe wheels, motors, maybe height, pitch stabilization, the host vehicle, or cutting arms. There are a variety of different applications that can be utilized. There will be body sensors, and there will be connectivity that might be a high-speed data bus or a low-speed bus or an RF link. So there could be a lot of different zones. There could be 20 zones, depending on the complexity of the type of vehicle that you're utilizing. But they'll all kind of be oriented in this way and shape. This is more of a low down and dirty to give you the basics of what it's going to look like. But regardless of the specific zonal architectural module, high quality power is needed, and ensuring high quality power is typically achieved with bulk caps, high-speed decoupling caps, and possible broadband capacitors, which are configured as an inline miniature EMI filter since they have 3 terminals. Just to give you an overview of all the things that could go into the power section of these modules, and we will talk about them later in this presentation in more detail when we come to them. And there's also, you can see a circuit diagram at the bottom left of this screen. I want you to pay close attention to that because that is going to come up later with some of the parts that we have to kind of optimize these power trees that you would see for an FPGA or an IC, just a controller in general that you would have at each module. Especially pay attention to the core power bank, and those decoupling capacitors. But it just gives you a brief snapshot of kind of how your zonal architecture will be oriented, and then also, what type of parts typically that you could put in here, down there in the bottom right area. And from what we can see in this slide here, you have a very bare bones block diagram of the power distribution of one of these zone modules. It's just a low down dirty example. Real world examples are going to have a lot more going on, but this is something easy that you can kind of look at and see what types of parts are going to be utilized in these areas. So you see underneath power distribution, you're going to have your zone module, which is your ECU, and then you're going to have a connectivity portion. Your body, window, mirror, locks are all going to be in a separate portion coming down from the tree. And then you're going to have your powertrain, motor, stuff like that. And then your EPS, your electronic power system. So this is a very typical example of what it would look like. But basically, we're doing a power conversion, typical buck at each module. And then so bulk capacitors, maybe high CV MLCCs or tantalum polymers, or aluminum electrolytics will be in these areas. For the most part, this is just a really easy kind of example of what you would see in one of these modules. And then on the block diagram to the right, if you have good enough eyes, or if you can zoom in, you can see all the different series of parts that Kyocera AVX has in play that you would put in those specific areas.
No matter what part of the system we're at or what that particular module is doing, then certainly power has to be a key component of it, and the quality of that power is going to be super important.
Right. That's the name of the game, is power stability, right? You want really high quality power in there. In order for your ECU to be optimized and to work as fast as it can, you're going to need stable power. And that's kind of what we specialize in, are bringing parts that will allow you to have stable power and a really good signal. Just to key in on that, the caveat, the next block is a subsection of that power distribution block that we just showed previously. So this would be like a typical power steering control module. Once again, this is just kind of a skeleton. It's bare bones, but it gives you an idea of what parts would go where. So if you're an enthusiastic design engineer, this would kind of highlight where you would go for a series of parts, or what you would be looking for in this section of the zonal module. Some of the blocks may be a lot more involved based on the application, but this gives you the bare bones of the types of components that will be seen. But the actual end module will vary a lot. Not too much to go over on this one, just kind of give you a snapshot of what will go in there and what we have to offer.
I have a question. In the upper right corner, you have some things about the series grade. You have standard and automotive. Is there some places in an automobile or an automotive application, you were talking about commercial vehicles now, that you can use standard components?
So that's kind of a loaded question. So in theory, yes, you can use, your commercial grade, your standard grade MLCCs or parts in general. And some, I'm not pointing any fingers, but some manufacturers will utilize them. And most of the time they'll work perfectly fine. But we would always advise that you would go with an auto-qualified part for a vehicle. One, because, you have kind of like a chain of custody, right? So when you have an automotive qualified part, if there are any changes to the designs of the parts themselves at all, you would have to be notified. So if we just changed the formula on the dielectric on one of the caps, we would then have to notify you or the manufacturer of the change. And then, you might say, well, hey, I'm not cool with that. I would like to have some batch testing done, get the electrical data and try to see what's going on. Which if you have an automotive quality part, then you're going to get all of that data and you're going to have that sequence of events of what's happening with the part. If it's just a commercial part or standard part, you won't have any of that industry-wide. So if you go with the standard part, you're really kind of rolling the dice. We have these up here because there are some areas of these blocks that maybe you don't need an auto-qualified part. Maybe it's not a high-quality area that you're super focusing on. Or, we all know people are trying to cost reduce in a lot of areas. That's one way people can do it. We definitely advise against going with commercial parts for automotive applications, especially depending on the application within the vehicle, but we have them, people want them, so they are there.
Well, that was a helpful answer to me because I was thinking just in terms of the specifications, the temperature range or the reliability, but that chain of custody is something I wouldn't even thought of. So that's a helpful answer.
Sure. And so this next slide is just kind of giving you another brief snapshot of the types of technologies that we have to offer. So, you're going to see your X7Rs, X7Ts, X8Rs, just letting you know that we have all of the different types of dielectrics, all of the form factors, the capacitance ranges, and then kind of the other different like interdigitated parts or reverse geometry parts. We have all of these that we have on offer, and they each have their own intrinsic kind of values that they bring to whatever your application is. We've highlighted all the automotive ones. Obviously, like we said previously, great question that you had. We advise automotive rated parts for automotive applications, but just to kind of give you an idea of the electrical characteristics of the parts and what we have to offer. And now we're moving into the tantalum versus tantalum polymer comparison. Now, in reality, what you're going to see in these applications, because power is so important on these little power trees that are in the zonal modules, in bulk power is what you're going to use tantalums for, right? Any bulk power needs. Typically, you use either a tantalum or an aluminum electrolytic, but aluminum electrolytics are not so reliable in the sense that they wear out or they dry out, but your tantalums are going to be super reliable, super long lasting. And then the tantalum polymer, as you can see from the charts below, you're going to get really awesome characteristics. We have high temp characteristics that go up to 150 degrees C for applications that are under the hood or maybe some downhole drilling or something that you have, really, really high temperatures that you're going to have to operate in. But especially under the hood in vehicles, it gets pretty hot. They have better reliability, smaller, lighter than alternate, capacitor technologies. Tantalum is the most dense technology in regards to capacitance per unit volume. The tantalum polymer is utilized here in a lot of these power trees because of the low ESR, which is necessary for high power applications. So when you have them next to these, computing for these ECUs, and all these next gen ECUs are faster, more powerful, beefier, controlling more tasks. Well, they're going to take their power hogs. They're going to take a lot more power. So you're going to need these bulk caps to kind of supplement. You can also use them as smoothing capacitors after converters. There are a lot of uses for them, but especially for power conversion with high current demand and motors, the tantalum polymers are going to be great fits. But this fits into zonal architecture theme based on the fact that you have localized ECUs, like I talked about before, throughout the system, which necessitates the need for smaller, lighter, high power density capacitors. This is actually one of my favorite parts to talk about because it just seems really cool, especially when you're talking about kind of fitting these ECUs and a lot of these actives and even in passives and everything in these small areas in the zonal scheme. You're fitting a lot of stuff in a very small space. So size is kind of king here. Wherever you can reduce board space or reduce the bill of material list that you have to order is awesome. And we have a part here in these 3-terminal capacitors, the feed-through capacitors, where you can reduce space. And this is where I was referring to in, I think, the second slide that we talked about, the circuit diagram that had decoupling caps. Pretty much in every power line, VDD, the power in, power out, you're going to have a decoupling cap. And for the most part, what's really used in a lot of occasions is where you can see on the bottom part of the slide, you'll see where it has the 4 capacitors in parallel with one another coming off of a power line going into an IC. That's in order to get a good power quality, stable power. So you're filtering out all of that noise. And the idea of putting 4 of these down there is so that you can get a really broad area. So you can pull either low transmission noises, low AC noises, or high frequency noises. So you need multiple caps down there so you can kind of reach all of them. You can kind of get rid of all the noise that's coming in and have really stable power. Well, typically what you would either do is either have a leading ferrite bead, like you see in the very middle section there. You see a red square and then 3 caps after that. And that's to essentially give you high frequency, low and high frequency broadband filtering. Or you have the 4 caps that's below that where you're filtering out a broad frequency. Well, what we can do is you get rid of 4 parts and you replace it with this 3-terminal capacitor. And it's 1 part that does the job of 4. So it's really neat. They have really, really great specs. If you look at the graphs down below them, you can see that blue line on those curves is the 3-terminal, the feed-through capacitor. So the graph in the middle and all the way on the right, you can see the other 2 lines that are on there. The red line that you see on the graph is with a ferrite bead and 3 caps. And then the black line almost directly mimics that red line on the graph. And the black line would be those 4 caps in parallel as well. And what you can see is the blue line there with that feed-through cap, you get a really smooth bathtub curve and you have the same frequency, maybe a little bit more of frequency that you're filtering in. And that's 1 part that's doing the job of, 4 discrete parts. So it's really neat. It's great for space saving. It's great for filtering. They just kind of do a lot of jobs as a one-shop stop. I really like them. They work like a broadband filter due to their reduced parallel inductance and increased series reductance. And there is no electrical component equivalent that I know of in this form factor. So it's a really neat part.
So you say there's no electrical component that's equivalent to this. I'm trying to think about this as an analog circuit designer in my background. Is how would you simulate that? Is it just a capacitor in the simulation? Is it a combination of a ferrite and a capacitor in a simulation if you're trying to see how this is going to react? What is the circuit model?
Right. So the equivalent circuit is a series inductance and a parallel capacitor. So you'd have an inductor in series and then a parallel capacitor. That would be how you would model that on LT Spice or something like that.
Interesting. And you get all that in one tiny package.
One tiny package. That's why I love this part. It's really neat.
I had never heard of feed-through capacitors before. At least I've heard it, but never dived in to see what they do. And so this is really fascinating to me.
And moving on here, you can see we have a variety of low inductance parts and geometries, footprints that we have to offer. From the top of this slide, you can see these are all essentially the same size part. They're just reverse geometry. So you have the standard 0805 MLCC, which is somewhere around, approximately 600 picohenries for the equivalent series inductance. And then you see the next part, the LICC, which is, it's basically you just flip those terminations and put them on the side. And you're dropping that inductance by, a factor of 6. So, it's really neat. And then it just keeps getting smaller. We're able to mess with kind of the terminations, the electrode patterns, stuff like that. And we're able to get all the way down to around 27 picohenries, just based on the geometry of the part. These are especially applicable when you're talking about having all of these ECUs right at the zones. So high frequency decoupling is going to be a very basic need that you need to fulfill in the zonal architectural layout. Due to the increased communication speeds, higher processing speeds with the ECU, and overall increased power load magnitudes. So low inductance MLCCs, they have the ability to quickly dump their charge to the load, maintaining voltage stability throughout various operating environments. And in some instances where you're going to need maybe a smaller MLCC, so when you're switching really quickly, a lot of times, if you need to power a transistor or something and you need a stable, fast power, right away, before your bulk caps can kind of catch up and supply a more sustained power, these are where these low inductance MLCCs really come in handy because they can supply power very, very quickly to allow you to, whether you're opening a gate or you're activating a transistor, and then it'll allow that to have stable power super fast until the kind of your more bulk capacitance power areas are able to keep up and maintain that. But they're really, really great. But this slide in a nutshell is just showing the low inductance MLCCs would be placed in a circuit, and it provides comparison of each type or low inductance MLCC response. So you can see on the right in a typical application of where you would see these low inductance MLCCs on a LiDAR driver stage diagram. So you might have a LiDAR application or sensor in your specific zone. So you're going to want your lower ESL MLCCs in those areas.
Well, Ryan, you're highlighting two of the challenges that are converging. The power is going up and the switching frequencies going up, making these just more ringing, more edge noise, more instability. It's impressive to see you guys reducing ESL in this package by a total factor of 20 or more, from that 600 picohenries down to 27. So it's a real advantage to system designers to be able to apply these and deal with those high current, high edge transients.
Right. Everything's only getting faster and hogging more power. So it's definitely something to keep your eye on and just to know, have a tool in your tool belt that you can throw at whatever circuit you might need to.
Yeah, and that's exactly why we love having these tech chats and having guests like you, is to get these tools into the tool belts of the engineers out in the field.
Right. And here we have another highlight of our parts, tooting our own horns again. Anywhere you would use your IGBTs, your rectifiers, any of these diode modules we have. So a lot of the times you're going to find these anywhere you have a motor. Most of the time you would use these to convert either AC to DC for other applications. But for automotive specifically, they would be used to step voltage down, usually as a DC-DC converter. So typical applications would be, if you have like LED lighting or anywhere where you have a motor with an H bridge or a full bridge, these modules come in handy. But this is more for high power converters or drivers. Anywhere with a half bridge or a full bridge driver, you would use these rectifier modules. I'm almost 100% certain we have automotive qualified modules. I would definitely want to recheck that. But if we don't have them yet, they are on the horizon if we don't already have them in the catalog.
And one of the things here is, you've been focusing on not just traditional automotive, but commercial vehicles and like agriculture equipment. Those are going to have, higher power requirements, but they're also going to have more motors, right? So that the sheer number of motors that are going to use these kind of components is going to increase.
Correct. And you really have to worry about, that those inductive loads or the feedback coming when those motors kick on or kick off. You need a way to kind of protect the rest of the circuit. So it's a great thing to have. And here we're just kind of talking a little bit more circuit protection with the different diodes that we have. So we offer, KVX has low loss, high speed shockeys. Pretty much if you're into circuit design, you're going to need some shockeys all over the place to protect the rest of your circuit or your load, or just, to direct power rectifying. We have shockeys, we have rectifiers, we have fast recovery diodes, which I think they're all automotive qualified. The fast recovery diodes are great because they just, especially with the high frequencies that everything's kind of switching at, you need something that's going to clamp or operate at really high speeds. So these are another tool to have in your tool belt, just to kind of let the world know, hey, we've got them, come and buy them.
Ryan, we've been talking about power distribution and all these great things we need to do to control the power, but in these automotive and vehicle applications, safety is a big thing. If we're talking about ADAS and automated driving, it becomes even more important. Can you speak to that a little bit?
Sure. That's a great point, and kind of why we're getting into this topic. Safety is more important than ever. We kind of have the actives now inside of all these vehicles that allow us to have a better grip on safety, whether it be driver safety or passenger safety or keeping the road safer in general. So we've got a lot of parts that can kind of go around those areas. And then not only that, but safety devices that can also protect the rest of your circuit or the rest of, your vehicle, whatever you just spent X amount of dollars building or purchasing, we want to keep it working safely. Here we have our ESD Safe MLCCs. Now, these are not to be confused with safety caps. We do have safety caps and we do have safety film caps, X1, X2, Y1, Y2 rated caps. But these are more for what you would utilize on maybe a human and machine interface, so a touchscreen or LEDs or ADAS. These areas, you would want to look at an ESD Safe MLCC. I think the last that I checked, you need to have a rating of, I think 2.5 kilovolts is what the body can hold as just a static charge. So when you touch that touchscreen of your vehicle or you touch the hood of the car or whatever it may be, you're discharging quite a bit of energy. You really need to make sure that you have ESD Safe caps in place. And you can kind of see from this graph, it's pretty neat. You can see the black line on this graph is showing you an ESD strike. So the one on top, I think it's 2 kilovolts going down to 8 kilovolts. So you can see The black line is showing the ESD strike without any protection at all. That's just it going straight into your circuit. And then with the blue line is the ESD Safe capacitor on that first one. So it's mitigating that entire strike and just absorbing it, eating it up, and keeping the circuit safe. And then for the 2 kilovolt, which is one I would be particularly of interest, the 2 kilovolt and the 4 kilovolt for your human machine interfaces, you can see that the blue line is an MLV. So it's a different technology, but still a multi-layer varistor. And then you also have the ESD Safe cap with a red line, and it is mitigating that entire strike. And these are very important because you spend all the money on the actives and the touchscreen and all of this infotainment, all of this really neat high-tech stuff that we have in our vehicles. You know, you want to protect it from your fingers or, you know, any other ESD strikes, any residual transients that are coming through. You want to protect your circuit, keep it working safely. So, you know, we have really small sizes. I think we go down to 0402 on the ESD Safe. It's showing 0603, but I'm pretty certain we can go down to an 0402 high CV as well. But these are just great parts, and it's great to really just know. And most design engineers, I would say, they know they need to protect against the ESD strikes and the transients, and it's just a really neat part and a small form factor that you can throw in there and keep the circuit safe. So here we have one of the staples to an ACQ 200 part or an automotive qualified part, and that is FlexiTerm. So FlexiTerm is basically just making sure that you have a capacitor that can withstand the vibrations, the shock and vibe environment that we're going to get out of either a vehicle on the road or the heavy vibrations from your big farm vehicles going through a field or whatever that might be. And all it really is essentially what it says. It's a flexible termination. It's a silver flexible epoxy that goes between the nickel and tin portion of your terminations. And it just allows it to absorb some bend and some shock. And you can see the bend tests here. I think a typical bend test for just a normal MLCC has to survive a 2 millimeter bend test, while the FlexiTerm has to survive at least 5 millimeter bend test, and even higher for certain geometries, but at least minimum 5 millimeter bend test. So you're getting a lot of extra flex out of that part, and it's just going to maintain its value and its properties for that much longer under austere conditions. And that's basically it for the FlexiTerm. It's nothing crazy. It's just kind of a novel approach to making sure your parts can sustain shock and vibe. With the Flexi Safe, we go a little differently here. You can actually see that bottom set of capacitors. You can see the electrode design is different. Here you have a floating electrode, honestly, between two capacitors in series. So you've got a floating electrode in there. So it's the same termination with a different electrode pattern. We call it a cascading pattern, which means there's a floating electrode in between the alternating electrodes, which creates an equivalent circuit of two series capacitors to provide redundancy in harsh thermomechanical environments. All this is to reduce the short circuit failure mode of MLCCs. So that's the big nasty failure mode that we've all come to know, is that short circuit. So this is to mitigate that.
So that's really interesting, Ryan. So you got two capacitors in series built into one package, and it just is a clever design. Again, another tool for people to have in their toolbox, and particularly for these long-term, as you mentioned here, and high reliability things, because yeah, failure as a short circuit is really catastrophic in a lot of applications.
Correct. And that's what we're trying to mitigate here. And they do a really good job of doing just that. And here we have a slide showing you maybe not so much safety, but protection, right? I consider circuit safety or circuit protection definitely a form of safety for the driver and passengers as well, because if something fails while you're operating, you don't know what will happen. So keeping your circuit safe is essentially like keeping your body safe or your vehicle safe. But it's really critical to keep your circuit safe and to mitigate transients that come through the circuit. And that's where MLVs kind of shine. They kind of go hand in hand with TVS diodes, but what you can see here on these diagrams here, your typical orientation on a bus line is you would have two TVS diodes parallel alternating directions, and then an EMC cap parallel with that as well. And what you can see with the MLV is you can get rid of all three of those parts and just supplement it with one part. They're going to do the same job. I will say TVS diodes do typically have a tighter tolerance from the clamping voltage to the operating voltage. So there are going to be some instances where you have to use a TVS diode. You're not going to be able to cross with an MLV. But for the most part, MLVs are going to be a really, really good way to go, because they can just absorb so much of the overstrike over and over again. the whole dielectric, essentially the whole area of the MLB will absorb the strike, whereas when you're talking a TVS diode, you just have one small NP, or if it's a bidirectional diode, you've got two separate die that have an NP that will absorb the strike, and it's not a lot of real estate to absorb it. So the wear out mechanism is gonna wear out much faster. They don't operate well under high temperatures. So you have to derate. Honestly, at the second you go above 25 degrees C, you've got to start derating those TVS diodes because they just don't do well under heat and humidity. Whereas the MLVs are great. You're not going to see any dip in performance when you go up in temp. Just something to keep an eye on. Keep your circuit safe, keep those transients out, look out for some MLVs. And here we're kind of putting supercapacitors in the safety electronics portion. A lot of that is because when you have your terminal 30s or your SOS buttons, your safety measures, you need an uninterrupted power supply. It's going to be discontinuous, but there is essentially with supercapacitors, you can charge and discharge these things till the moon goes away. You could just continue to charge and discharge them. But with batteries, they're going to degrade over time, or they're going to drain, or they're going to have issues with a battery. So a lot of times you're going to want to put a super cap or, maybe even a Tanum in there. So they're just super long lasting and very reliable parts. And we do have automotive qualified, ASQ200 qualified supercapacitors for the safety factor in here. But this is a big deal because many zonal architecture systems do not have constant power draw. They have discontinuous loads. They also might have a need for hold up if power gets disconnected. Say with a lot of vehicles, if the battery's dead, especially with EVs, the battery's dead, you can't open the door. So if you need to get out and you can't, that's a problem. Some novel approaches are you put a super cap in on that module down where the doors are. You have that burst of power that'll be able to unlock your door or roll a window down or whatever it might need to do. Super caps, they can deliver that. They can deliver such high levels of current, they greatly eclipse batteries as a power source. For instance, if you have a super cap about the size of a Coke can, you can get about 1,000 amps out of that capacitor, enough to melt and weld pennies together. So I don't know why you'd need to, but you could if you needed to.
Yeah, you probably don't need to melt pennies, but your application of being able to unlock the door is a real thing that I saw in the news recently about an EV car that they could not unlock the door after the battery went dead. So it is a definite real concern and a real application that people should be thinking about.
Right. Now, it's definitely helpful to note that batteries greatly eclipse supercaps as like an energy source. There's a very large difference between a battery source and power. So with power, you're getting instantaneous current, boom, right to wherever you need it to go. Whereas energy source is more of you can continually draw low power for a long time, right? So that's kind of where they differ. But we also offer modules. So UPS modules, uninterrupted power source modules, made here in Greenville. The modules designed here, the whole system is. If you're sticking in the commercial vehicle realm, if you needed to run, say, a refrigeration truck and the battery dies and you need some supplemental power, you've got a module, I think it's 48 volts, that you can run that refrigeration module or whatever it might be, generator, whatever you need it to do. Just know that it's out there and you can really kind of be an engineer and figure out new approaches to kind of sustaining power when you need it. And safety caps, the supercapacitors can definitely fit the bill. And so here, once again, not going to talk too much on this slide, but it's just another down and dirty block diagram of a Class 8 motor drivers or the body control module block, just to kind of let you know what goes in there. So it's under the ECU. You'll have that body control. It'll control your motor section, whether it be the motors for your windows, or maybe a motor for a winch, or a motor for one of your doors, one of your rear doors, or something like that. This is kind of what it will look like. And once again, when you actually go in there and you start designing this, it's obviously going to be a lot more complex, or it could be this simple, depending on what your application is. This should give you a basic snapshot of what to look for and where to look for whatever series of parts that you think you might need. It's just kind of a nice little chart to give you an idea of where to go. And here we're maintaining the theme of protection and motor protection. A TVS will protect against transient strikes or an MLV, but you also need a cap to filter out the noise going to the motor, which brings into play the cap guard that you see at the bottom there. A noise can occur on the VCC and ground lines in either direction, in both directions. So you have what's called a general noise or a differential mode noise that can be filtered out using the cap guard. Then at a certain point, you're going to get that general noise that we just talked about, that differential mode noise, and then what's called a common mode noise, where the common mode noise and the general noise and a transient strike all kind of come together at one point because these motors have an inductive load that cause transients. That's where we introduced this AMTS part. It's a newer part. It's a pretty neat part, which will protect against all of these sources. So once again, going along with the theme of reducing the amount of components that you need for whatever the occasion might have, not only will it filter out your common mode noise, it will filter out your differential mode noise, and it will also protect against transients. So on this slide, it's a little easier to see what's going on with a cap guard, just a regular MLV versus the AMTS, the new part that we're kind of unveiling. With the cap guard, you will basically have a single EMI signal that you're suppressing. But with the AMTS, you're able to hit multiple lines of communication, or you're able to protection on multiple lines. What it is we're just essentially using our expertise in the stacking technology to combine MLVs with MLCCs in a single package. Once again, save board space and just optimize the board and optimize the circuit. It's a radio package, so the termination can be placed as close to the motor as possible, because that is kind of key when you're trying to eliminate transients. In the circuit, it will suppress transients and also have EMI suppression from the MLCC. So you're kind of killing two birds with one stone here. It's just another way to consolidate discrete components into a single package, which is kind of the theme that we've been hitting on here. As we all know, board space is king. But that's pretty much it. You can look at the graphs and kind of see where it's going with it and everything that it can do. And we're pretty excited to roll this part out.
It's a reminder to me, Ryan, of the engineering that is kind of inside the engineering. All the high-level stuff gets all the attention, but the amazing engineering, and that's packaging engineers and all the technologists that build these things ever smaller and ever more complex. They're kind of the hidden secrets of the amazing world of engineering.
It really is neat to see, especially when you see how far capacitors have come from the sizes that they used to be. And now you can look at them on a table and they look like, salt and pepper just sitting there. So it's really neat to see everything shrink, but still get, high quality parts and really great electrical characteristics from them. So I agree. It's really neat to see. And this is just another snapshot of another little control unit, navigation control unit, something else that you would see in one of these zones. And once again, just to give you an idea of the types of parts that we have that we can. I think the new wrinkle that we've thrown into the navigation control unit are the antennas. And I won't speak too much on the antennas, just to let you know that we do have them. We have an antenna that will fit any need that is out there. And we have all the different form factors as well. We'll get into that down when we roll into the antennas. Almost all the technology is kind of filled here. So we've got quite a vast portfolio to look from. Here we have clock oscillators. We have regular crystals, we have clock oscillators, we have oven controlled, we have every crystal that you can think of. We've got them all, but I really want to talk about the importance of the clock oscillators and the crystals themselves within this zonal architecture platform, because we have power trees that we're going to place in each one of these by these ECUs, which we can get them super close to each ECU, which is of great importance in itself. But now we were able to put high accuracy, timing, stability in these systems. So I like to think of the clock oscillators as a way to keep the noise at a minimum, right? So if you can think of a symphony, and if they are all kind of on their own frequencies and doing their own thing, it's going to be really noisy and nobody's going to want to pay money to go to this symphony. But once you have a clock sitting right there that is keeping everybody on the same page, especially if you can get it as close to the ECU as you can, you just have a lot of stability and accuracy in each ECU, which allows you to have really high performing ECUs and performing quickly. So it's just a really great part to have close to your ECU, have close to each zone. These specific crystals have a really low jitter, so they have very high stability, and really they don't have a huge wear out mechanism. They last for a really long time. That's due to Kyocera's manufacturing process, growing really high quality crystals and keeping everything as clean as possible in the process of combining them. And you have any footprint that you could possibly want, as well as they're all ASIC 200. So it really fits the needs of the zonal architecture systems. And then here we have the antennas in our portfolio, as I was speaking to before. And this is, once again, just another snapshot. It's difficult to get into the weeds with the antennas in such a short window of this presentation, but this is just to let you know that there is a footprint, there is a technology, whether you want stamped metal, ceramic, chip. We have patch antennas, multi-band antennas. We have any antenna that you would need for whatever occasion you might need. And this goes hand in hand with all of the V2X, V2V, V2I, all of the positioning needs that you need and all of the communication that needs to happen with these vehicles and even autonomous vehicles. A lot of guys are mowing or are harvesting crops from a chair in an office, driving a combine. Connectivity is key, and this does go hand in hand with the crystals that we spoke about earlier, keeping good time, having good proper communication. And this ties in having these zonal systems set up into different areas, reduces latency, and allows you to communicate more quickly and have less noise with premium parts. To tie it all in together, it's pertinent that we end with antennas.
Well, Ryan, I want to thank you for your time. I know I learned a lot today about not just the zonal architecture, but just all the components and the advanced engineering that Kyocera AVX is bringing into these systems.
Sure, absolutely. I really appreciate you having me on here, Dale. Honestly, I wish I had more time to get into the nuts and bolts of everything, but this is where we are, and I'm excited about the whole zonal architecture theme. I think it's really neat. Really excited to see it come to the market, and I think we have a lot of components that can fit the bill. So thanks for having me. Thank you for your time.
Before we end today's Tech Chat, we want to thank our friends at Mouser Electronics. If you're looking to purchase any of these great Kyocera AVX products, please head over to Mouser.com to help them continue to support educational presentations just like this one. And join us again next time on Tech Chat, where we chat with the leading technical experts like Ryan Messina from industry-leading innovators like Kyocera AVX who are changing our world every day.